Hello, and welcome everyone to the latest City, University of London, European Social Survey and NatCen Survey Methods webinar. This is actually our 50th Survey Methods event since the seminar and webinar series started in 2017. The first 22 were in person and the last 28 have been online after we switched to virtual sessions during the pandemic. I'm Tim Hanson. I'm a Senior Research Fellow at European Social Survey headquarters in London, and I'll be chairing today's session. We're very pleased to welcome Stephanie Eckman, who will be our speaker today. Stephanie is a researcher and data scientist at the University of Maryland's Social Data Science Center. She has a PhD in statistics and methodology and has worked in survey research for more than 20 years. Today, Stephanie will be presenting on the very interesting topic of bringing survey methodology to machine learning. Stephanie will talk for the first part of the hour, and there'll be lots of time for questions after that. If you do have any questions, please type these in the Q&A area and we'll go through as many as we can. So I'll now hand over to Stephanie.
Excellent. Thank you very much, Tim. I'm really happy to be here and to be the 50th speaker. I have not been able to attend too many of these series of the webinars in this series, but I've always seen the announcements, and you guys, it looks like you guys have had some really interesting topics, and I was sorry I couldn't make it. It is a bit early here, but I've made an exception and gotten up and dressed up a little bit for you for this presentation. I'm really happy to be here. Thanks a lot. I'm going to talk today about bringing survey methodology to machine learning. I'll explain what I mean by that. But first, I want to acknowledge my co-authors. I think I can get my laser pointer here and point to things on the slides. Yep. So I'm working with several researchers from a university in Munich, LMU. So Christoph, Jakob, Bolle, and Frauke are all at that university. And then Rob Chu works at RTI International. And when we started this work, I was also at RTI International. And so that's how we got, that's how I got connected with him. So this is research that we've been doing for the last couple of years. And we're trying, as this title says, to bring survey methodology to machine learning. And what I mean by that is, you know, you may have seen talks at the conferences like APOR was recently held, and a lot of people are talking about how can machine learning improve survey research, right? And so people are doing things like using boosting methods to fit propensity score models, or using NLP methods to analyze open-ended texts. There's a talk with some work that I did while I was at RTI. One of my RTI colleagues presented work about using machine learning to grade recorded telephone interviews and tell if those interviews sort of meet expectations or don't meet expectations. All of that is really interesting and exciting work. I'm excited about the things that machine learning can do for survey methodology, but what we wanted to do with this research project was turn the tables on that and say, hey, you know, survey methodologists, we have things to contribute to the world of machine learning as well. And so that's the research that we've started to do. It's still early days. And that's what I'm going to be presenting to you guys here today. So some of you may recognize this man. This is Sam Altman. He is the CEO, I believe, of OpenAI. OpenAI is the company that has created those large language models you've probably heard about. So GPT-3, ChatGPT, and more recently, ChatGPT-4. So this company is the ones that creates and trains and releases those really large language models that have done some really amazing and exciting things and also some really strange things, right? I'm sure you've seen the news stories about sort of the way that these models work and sometimes do not work. But all of those models and similar ones by Google and Facebook and other companies like that, right? They're all based on labeled training data. So they use data from the web as training data. And then the more recent models like GPT-4, they actually had people sit down and give the models feedback. So the model would return something that it thought was relevant to a prompt, and somebody would sit down and manually code, is this result that I got from my prompt relevant? Is it correct? Is it ethically reasonable, right? So these models are really based on just terabytes and terabytes of labeled training data, which ultimately comes from humans. And so on this podcast that I heard recently, Sam Altman was talking about what does he think is the big problem or the big challenge to pushing this research forward. And what he's really concerned about, he says, is the bias of these human feedback raters. So the bias in this labeled training data that's so important to the training of the models that they do at OpenAI and across the industry. So this really struck me because, of course, that's what we do in the field of survey methodology is we collect data, we collect these types of labels, right? And so if this is what he's really concerned about, that's an opportunity for all of us in the survey methods field to step in and say, hey, we know a lot about data collection. We can help you collect some labels to improve your models. That's what we do. So if we think about the survey process that we generally, spend our days concerned with and talk about at our conferences, we start with like a survey question. Here's a very general health question, very commonly asked in the United States. You probably asked this one as well. Would you say your health in general is excellent, very good, good, fair, or poor? And so we're showing here what this looks like in a web survey. You might choose fair and then click next, right? And when we ask questions like this, we worry about non-response, we worry about order effects, we worry about interviewer effects, not in a web survey, but in other modes of surveys. So we worry about these kinds of things because they can impact bias in the estimates that we make, right? So we might worry like, oh, my response rate's only 30% or only 5% or whatever it is these days, right? That non-response isn't so much a problem itself. What we're really interested in and worried about is the downstream effect of what does that non-response do to my estimates, right? If I publish an estimate saying this many people are concerned about global warming, is there bias in that estimate because the people who aren't concerned about global warming maybe didn't do my survey or something like that, right? So we've got error sources, and then we've got the ultimate impact of those errors, which can result in bias or variance in our survey data. And I'm drawing this out because I think there's a really nice parallel to what's going on in the machine learning field. So they use data collection instruments that look like this. This is developed actually by Rob Chu at RTI, one of the co-authors on this presentation. It's a little small, I know, but basically what this is doing here is presenting a tweet. Glad today is a short day instead of a regular shift because my head is hurting. I need new contacts. I lost my glasses again. So this is a tweet that they've pulled off of Twitter. And then the annotator should indicate whether this tweet is positive sentiment, negative sentiment, or neutral or skip, which I think is essentially I don't know here. So this instrument strikes me as really similar to the survey, to the web survey, right? You're given sort of a statement or a prompt, and then you're given some closed answer choices, and you should indicate which one best applies. Now, the health question asks the respondent about themselves. And this one here asks the annotator about something completely external that they've never seen or thought about before, some tweet that they've almost certainly not read, right? But the format and the appearance of these two things is very similar. And so what we did last year in our APAR presentation and in our paper was we looked at whether some of the common effects from survey methodology that we know affect sort of opinion questions or these kinds of questions in web surveys, do they also affect the labels that we collect with these kinds of annotation instruments? So we looked at wording effects, we looked at order effects, and we looked at annotator effects. And we found evidence for all three of those in a study that we did last year. And that was the end of that study. We just sort of showed, hey, it looks like some of the effects that we see in survey methods replicate in the annotation field. And what we want to do now is this next step, right? We know that these kinds of effects can occur in annotation or in labeling. I'm going to use those two words interchangeably. But what we're really interested in perhaps is what does that do to the models that we train? Would we train a different model because of these wording effects and order effects and annotation effects? And so this is the piece that I'm going to concentrate on today and that we're doing in this new research project. I should say this work was presented recently at APAR by my co-author Jakob Beck, and we are working on a paper and we should have that done by the end of the month. So the research design that we used here, we again worked with tweets like we saw in that previous instrument. We worked with a bunch of tweets and we had annotators code them as either containing hate speech or offensive language or neither, right? And we designed 5 different annotation conditions, 5 different versions of that annotation collection instrument. And the research questions we're interested in is, do these different conditions lead to different labels? Now, we think they do because that's what we did last year with a slightly different design. We showed that the different annotation conditions lead to different labels. So we want to replicate that work, but we're pretty confident that that's going to show up again. And then what's new this year is that we want to know if these different annotation conditions lead to different models. So would you actually train a different model if you collected the annotations in a slightly different way? And I want to remind you, we're really motivated here by the survey methods literature. As you know, asking opinion questions like you do in the ESS, those types of opinion questions are really sensitive to the order in which the questions are asked, or small changes in the wording. Do you favor XYZ versus do you oppose XYZ, right? You get really different answers to those questions. And so we want to see if those kinds of effects also occur in annotation, because as far as I can tell from reading the literature and the rest of us in this research group, nobody in the machine learning field is thinking or wondering or worrying about this at all, right? So there's a lot of research to be done here, and that's the kind of stuff we're trying to do. So let's look at these 5 annotation conditions in a little more detail. So I'm going to show you the 5 conditions stacked up here. This horizontal axis is sort of time as you go through the annotation task, right? And each one of these black rectangles is a screen in the annotation instrument. So in condition A, the annotator sees tweet number 1, and then codes, is this hate speech, is this offensive language, or is it neither? It's essentially a select all that apply question, right? So you see there's a radio button for hate speech, there's a radio button for offensive language, and then there's an option for neither as well. And so you can pick just hate speech, just offensive language, or both for each one of these tweets. So you look at tweet 1, you code, select all that apply, hate speech, offensive language. Then on the next screen, you see tweet number 2 with the same response options, tweet number 3, and tweet number 4. And our annotators in this study each did 50 tweets. So I'm not showing you all 50 here to keep the graphic reasonable, but there's 50 of these screens in condition A. Condition B looked a little different. We broke each tweet up so that it had 2 screens associated with it. So we see tweet 1, and we code, is this hate speech? Yes, no. Forced choice, yes, no question here. And then we see the same tweet on a second screen, and we code offensive language, yes, no. And then on the next screen, it's tweet 2, hate speech, yes, no, and then tweet 2, offensive language, yes, no. So here we've got 100 screens, but we're essentially collecting exactly the same information, right? You can see that these 2, condition A and condition B, and all through E as well, they're going to give us the same amount of information. We're just changing sort of how the task is structured or organized, right? So again, here we would see 50 tweets over 100 screens and collect this hate speech, offensive language information. Condition C is just like condition B, but we flipped the order of offensive language and hate speech. So we first do offensive language for tweet 1, then hate speech for tweet 1, then offensive language for tweet 2, and so on. And then condition D is a little bit different. Here we did all of the hate speech labels first. So tweet 1, is this hate speech? Yes, no. Tweet 2, is this hate speech? Yes, no. And on until you get to tweet 50. Is this hate speech? Yes or no? And then you go back and you're seeing tweet 1 again. So this is going to look familiar, right? I'm going to go see that's the moment where the annotator realizes, oh, I'm going to see all these 50 tweets again. And you see tweet 1 and you code offensive language, yes, no. And then tweet 2, offensive language, yes, no. And on until tweet 50. And then condition E, you might see this coming, reverse is the order of those 2 things. So in condition E, we again show all 50 tweets, just coding here offensive language, and then go back to the beginning and see all 50 tweets again and code hate speech. So those are the 5 conditions. As I said, they all result in the same amount of information. For each tweet, we have a label for whether it's hate speech, yes, no, and whether it's offensive language, yes, no. But they differ in sort of how this is organized. And we're going to use this orange-blue pattern throughout the slides to sort of remind you of what the different conditions mean. I hope that works a little bit, but if not, I can also remind you. So for the data collection, we chose 3,000 tweets from a corpus created by Davidson et al. And these were oversampled to be hateful tweets. So if you just go out to Twitter and you try to code hate speech, there's thankfully not enough hate speech to make that a worthwhile task. So these are quite hateful and terrible tweets. We then selected 900 annotators from the Prolific platform, which is sort of like an MTurk platform where you can just get people who will take surveys or do these kind of labeling tasks for a little bit of money. And we used only annotators who lived in the United States. We did this in November and December of last year. As I said, each annotator coded 50 tweets. And we did code each tweet and each condition 3 times. So we had these blocks of 50, but we had 3 people go through each block of 50. So we had 3 annotations for each tweet in each condition, 3 labels of all the tweets in condition A, and 3 labels of all the tweets in condition B, and so on, which meant that we ended up with 15 total annotations or labels for each tweet. That 15 is the 5 conditions times 3 annotations in each of the conditions. And in total, we have about 45,000 annotations of these 30,000 tweets. Now, this is not really the way you would do this if you were trying to really develop a hate speech coder. This is much more annotations that you need, but really we're trying to study, the difference between these conditions. So we needed all of this different kinds of data. So with this, we can, as I said, first of all, look at how do the labels differ by the condition? Do you get different rates of hate speech labeled in condition A versus B versus C and so on, or offensive language? And I'll show you those results. But of course, what we're really interested in is the downstream effects on the models. So to study that, we had to train many different models. So we took our tweets and divided them at the tweet level into a training set and a test set. The training set contained 2,250 tweets, and the test set the remaining 750. And then on this training set, we trained 5 models. So a model trained on just the labels collected in condition A. Another model trained on just the labels collected in condition B, and so on. So we end up with 5 models here. And then we can evaluate each of these against the test set, right? And we'll look in more detail into how that works. But so I've been talking about 5 models, but it's actually a little more complex than that because we fit 2 different types of models. So some of you may be familiar about these different types of models. We did one, which is an LSTM, that stands for long short-term memory. That seems a little strange of a name to me. But it's the long short-term memory model. This one was trained entirely on our data. Sort of, we created this model and we trained it on, say, labels collected in condition D. And that's all the model knew, was the labels that we had from condition D in the training set. The BERT model, on the other hand, is one of these large language models. It's already been trained on a bunch of information, a bunch of language and documents downloaded from the web. What we did was we fine-tuned it on our data. So we fine-tuned the BERT model, say, on the labels collected in condition E, and developed a model that way. So the BERT model sort of has a lot more knowledge sort of in the back of its head about how language and words work, whereas the LSTM has really only seen our data. So I'm going to talk sometimes separately about the results from these 2 different models. And then, of course, we have 2 dependent variables. We have the hate speech and the offensive language. So we've got 5 models for each of the conditions times the 2 model types times our 2 dependent variables. It gets a little complex. So we've got a lot of different results. I've tried to prune it down and show you a more reasonable subset of the results so that it doesn't get too confusing. But I have a lot more results. If anybody's interested, I can dig in, show you the paper and show you some of the other results as well. First, I'm just going to show you how the conditions affect the labels, because I do think that's really interesting. And I think already the machine learning field isn't looking at that and isn't aware of it. And so that's already an interesting finding. And then we're going to look at the performance of those models trained on each of the conditions. There's 2 methods of model performance that I'm going to show you. The first is the ROC AUC. This is the area under the receiver operating curve. This is commonly used with like logistic regression and other kind of these binary choice models, to measure model accuracy. There's a lot of different measures of accuracy in this world. We've picked the ROC AUC. You may have your own favorite one, but this is the one we're going to show. And then we're going to look at the learning curves as well, sort of how does that measure of model performance, that ROC AUC, change as we get a little bit more training data. And then I've also got a little bit of data about how the predictions of the models themselves differ. I grayed that out here. I don't have that in the main body of the presentation because I got some feedback that it was a little bit repetitive and a little bit much to take in, but I can show that if anybody has questions. And then, as I said, it's a little bit more complex because we've got all of these results by our 5 conditions. by our two dependent variables, hate speech and offensive language, and then by the two types of models, the LSTM and the BERT, so this is why I tried to prune back the result a little bit and not show you everything, because it's a lot to take in. Okay, so here is our first set of results, and this is just going to be the percent of tweets labeled offensive language or hate speech in these 5 conditions. And here you've got the orange and the blue boxes, which are trying to convey how these different conditions worked. Condition A, collected, was like a select all that apply on one screen. Condition B, first hate speech, then offensive language on the next screen, then hate speech, then offensive language. Condition C is the reverse. And then condition D is all 50 hate speech, and then all 50 offensive language, and condition E is the reverse of that. And then on the horizontal axis, you see, we're just going to see the percent of tweets labeled offensive language and the percent of tweets labeled hate speech. So here are the results. If we look just at the blue boxes in the left-hand panel, these are the rates or the percent of tweets labeled with offensive language in each of the conditions. I'm not showing you statistical significant stars here, but we did do that testing, and a lot of these are significantly different. We see that condition A collects many fewer offensive language labels than, say, B or C, right? Condition A is the one that was a select all that apply, and B and C had a separate screen for the offensive language condition. So there's something going on there that causes annotators to less often select offensive language in condition A than in conditions B and C. B and C themselves are operating very similarly, not a lot of difference there. If we look over at the hate speech column of results on the right, again, we see less hate speech in condition A than in condition B. The condition C maybe is in the between now and not right up there with condition B. But the takeaway here is that these conditions matter. Like, you collect different labels when you use these different conditions. And this, again, is something that until we did our paper last year, I don't think anybody in the machine learning field was thinking about. They're not like agonizing over how to structure these questions the way that we do in the survey world, right? Like, I don't know exactly how they do it, but they maybe think like it doesn't matter how you would organize this, the task, the annotation task like this. And so our work last year and again this year shows that it does matter. You get different labels when you change the way the instrument works. Probably isn't too surprising for those of you in the survey methods field, because we know that, we've known that for years, but it's nice to replicate it and show it exists in a different field as well. I just want to say one more thing about this, which is that we see more hate speech in condition D and less offensive language in condition D relative to E, right? So more hate speech in D versus E and less offensive language in D versus E. And these are the two where you saw all 50 tweets in one to code one of the labels, and then you flipped and you saw those 50 tweets again and coded them with the other label. And so I think what's going on here, it could be some kind of fatigue effect, right? So we're getting more hate speech when hate speech is first, and we're getting more offensive language when offensive language is asked first. And maybe by the time you get to the back half of the instrument and you realize, I'm going to see all those tweets again. And so you do less offensive language in the second half of the coding and less hate speech in the second half of the coding. So this to me looks like, we haven't really tested this formally, but we suspect this is a fatigue effect, or what I've in my other research called like a motivated misreporting effect, right? Like this is getting repetitive and boring, and I'm going to stop doing such a good job coding these things. And so that's why we see less offensive language here and less hate speech. Just a hypothesis, we're not sure about that yet. Okay, now let's move on to talk about model performance. And again, we're measuring that with that ROC AUC. If you're not familiar with ROC AUC, that's fine. It's just a number that runs from 0 to 1, where 1 is sort of better performance. And we're going to see some 5x5 graphs here. It gets a little complex, so I'm just going to walk really slowly through one row of the table and then broaden it out and show you the whole thing. So what we're looking at in this row here is a model trained in version E and then tested against labels collected in in condition A, B, C, D, and E, right? So a model that's trained on labels collected in version E and then tested on labels collected in version E has a ROC AUC of 0.85, which is quite good. If you can't, I know the numbers here are quite small. If you can't read these, we've color coded them. So like the darker the blue, the higher the ROC AUC. So in this row, the highest ROC AUC we see is when we take the model trained in version E and we test it against the labels in version E. I think I've got a little circle. Yeah. That's the highest performance measure in this row. The others are like 80% when we test against version A, 81% when we test against version D. So this model is doing a little bit less well when we test it against these other, against labels collected in the other conditions. Okay, now I'm going to show you the rest of the 5x5 table. Where is it? There we go. So this just shows you the rest of the data here. So a model trained on labels collected in version A, tested against labels collected in version A, tested against labels collected in version B, in version C, in version D, and version E, and so on, right? So this row is the model, the performance of the model trained on labels collected in condition B, the performance of the model trained on labels collected in version C, and so on. I think the first big takeaway, and that's what I'm trying to show you with these black circles, is I would have expected to see a really strong diagonal effect, right? That each model would do best when tested against labels collected in the same condition. So AA, BB, CC, DD, and EE, I thought we would see those pop out as having the highest performance measures. Other than row E, that is not what we see. We don't see the model doing best in those conditions. And in fact, we see really strong and surprising sort of column effects, right? So condition D is lighter blue. I'm sorry, that one right here, if we look at the column associated with labels, the labels in the test set from condition D, we see that it's lighter blue, which means that all models are sort of doing less well when evaluated against labels collected in version D. Even models trained in condition D are doing less well when evaluated against labels collected in condition D. In contrast, all the models seem to do much better when tested against labels collected in version E. So I found this sort of odd, right, that we're seeing these column effects and not the main diagonal effect. If we look at the same graph for hate speech, we again see some of these column effects. Column A seems to do pretty well here, but we also start to see some row effects. So the model trained on labels collected in version D tends to have higher performance measures than the model trained on labels collected in version E. It is a little hard to think about and talk about, and so maybe I'll just spend a moment, maybe I'll just have some water and you can look at this. I guess another thing to notice is that we generally see slightly lower performance of the hate speech models than the offensive language models. Hate speech is rarer than the offensive language as well, so that might be part of it. But these kind of row and column effects that we're seeing, especially in D and E, I think these are related exactly to that fatigue or motivated misreporting effect that we saw in the previous graph, right? There's something about these D and E models and the fact that they make you go through these 50 tweets twice that causes some problems on the second half when you're going through those tweets again. So we see that the model trained in version D is doing pretty well. Here it sticks out as having a darker orange color or higher performance metrics. And that's the one where the hate speech labels were collected first, right? And we see that E does well here in the column, or when we test against labels collected in condition E, it does well in offensive language. You've got the darker blue here, and that's the condition where offensive language was collected first. So I think we can start to understand some of these row and column effects. I can't claim I fully have my mind around these results, but I'm starting to see some patterns that make sense and relate to what we saw in the previous graph about the rates of offensive language and hate speech. So I don't think I mentioned, these are the LSTM models. This is the model that was trained solely on our data. It doesn't have anything else that it's basing its predictions on. But we can look here at the BERT models. So these are exactly the same kind of setup here, but now we're looking at the performance measures for the BERT models. And again, we see sort of a lower effect of offensive language in condition D, both in the training row And in the testing column, we also see something not great with condition A in both training and test here. There's lower blue here in conditions in the row and in the column. And then when we look at hate speech, again, we see sort of a darker orange color for condition E, and we see a darker orange color here for condition A as well. A couple other things to note, the performance measures are generally higher for BERT. So BERT is doing a slightly better job than the LSTM model overall. Yeah. Again, also, we see no diagonal effect. We don't see this sort of expected dark color, higher performance along the main diagonal, which I thought was really surprising. And then the last piece of results I have to share with you today are these learning curves. So what we're doing with the learning curves is tracking how that our ROC AUC statistic changes as we give it a little bit more training data and a little bit more training data and a little bit more training data. Before, we were just sort of showing you all the training data, all those 2,250 tweets and all the labels that we have for them in each condition. But now what we've done here is we've randomly chopped up that training set and we're feeding the models, and this is the BERT model here, just a little bit of training data at a time, right? Like spoon feeding a little more, evaluating the model, giving it a little more training data, looking at how it performs. And so you can see as you give it more and more training data, that's the x-axis here, you get higher performance, higher ROC AUC curves. That's the vertical axis. Now the thin light colored lines are showing you the actual numbers, which do bounce around quite a bit, but we filled them in here with like a smoother and a thicker line here so you can see the trend more easily. So when we have like just a very little bit of training data in the BERT model, it's getting ROC AUCs of about 60% in each of the conditions. And this is because, you know, it already knows a bunch of things before we even start training it. The BERT model, like, was, you know, it's a large model that exists before we even did this project, right? So it already like brings a lot of knowledge to the game. And so it's doing okay, even when we give it just a little bit of training data. And as we give it more and more and more training data, the ROC AUC increases. It looks like it, you know, reaches about 80% here, which is what we saw in the previous slides as well, the 80% ROC AUC. What I think is interesting here is that there's a real outlier in condition E. Condition E is the one where everybody coded offensive language for 50 tweets and then went back and coded hate speech for 50 tweets. So the 50 hate speech codings are at the tail end of that instrument. They're the second half of that instrument. And here we are looking at hate speech, right? So these are the labels where people may have been fatigued or annoyed that they had to go through and see all those 50 tweets again, which is an effect we have seen in surveys and some of the motivated misreporting work that I've done. So throughout the range here, this condition E is a real outlier and is slower to develop. It starts with a lower ROC AUC, and as we add more and more training data, it increases, but it's always lower than the other models, right? Even when we get out here to the maximum amount of training data, it's much lower than the others. It looks like this is not statistically significant, but it suggests that this condition E is really underperforming and not doing as well. And so again, to me, this suggests that it matters how you collect these labels, right? You can't just say like, oh, it doesn't, you know, sure, there's some small differences, but in the end, it all comes out in the wash. Like this suggests that it doesn't, right? You could feed it more and more and more training data, and this training set or this condition E model isn't really catching up to the others. And so you'd definitely, if you were training this model, you know, to really detect hate speech, you'd want to use one of the other conditions here, because those are the ones that are sort of indistinguishable in terms of the ROC AUC here when they get all the training data. So those are all the results that I have. Well, I guess as I mentioned, I have a bunch more, but I didn't want to overwhelm anybody. But for me, the big takeaway here is that how you collect these annotations matters. It matters not only to the labels that you collect, but it matters to the models that you train. Model accuracy, model performance, model learning. All these things are impacted by the ways in which the labels are collected. And as I said, I don't think that this is a result that anybody in the machine learning field is aware of or maybe even expecting. So we're excited about this. We hope to take it to some of the machine learning conferences later this year. That said, maybe it's not too surprising for this survey methodology audience, because we've known for years that these kinds of small changes in the way we ask questions can affect the results that we get. Some of the conditions perform better or worse as training and test data. We saw some of those strange row and column-wise effects that I'm still kind of trying to get my mind around. I think more research is needed to inform best practices. That's where we'd like to go with this, right? Is to give the machine learning world a set of best practices. If you're going to be collecting training data, these are the kinds of ways you should structure or not structure your annotation instrument for the most accurate labels and the best performing models. And we do see some evidence of fatigue or of motivated misreporting, perhaps, in conditions D and E, and we need to dig into that a little bit more. Next steps for this research, we plan to replicate this with other kinds of training data. As I said, this is our second study, and both of them have used hate speech labeling of tweets. We'd like to get away from that and maybe go into images or other kinds of annotation to show that these impacts replicate and apply to other types of data as well. And then in the past, so far in our previous two studies, this one and the previous, we've really carefully controlled and programmed how the instruments work in order to create these kinds of conditions, right? It's been difficult to do that kind of work because the annotation instruments, don't work that way. They have one approach that they want to use, and we've really tried to manipulate and carefully control the instruments. So I think what I would like to do next is to, instead of building in small manipulations of how the instrument works, I want to use some of the big name platforms like Labelbox and Label Studio and SageMaker and other ones like that. Those platforms have already made a suite of decisions about how the task annotation structure should look and how it should work, right? So I want to just say, like, well, let's compare then annotators using these different platforms and see if we get different labels, and then ultimately different models as well. And then I want to also, one of the things we're talking about is varying the annotators. So we've always done this like one pool of annotators that we randomly allocate to the different conditions. We could do it the opposite way, right? We could have one annotation task, but use different groups of annotators, where you could use Prolific, we could use mTurk, we could use Appen. There's lots of different, these groups around the world that where you can get annotators, right? And does that matter? I think there's a nice parallel here in the survey world to like a probability sample versus a non-probability sample, right? If you carefully control who your annotators are and whether they're representative, you get better data than if you just let anybody volunteer and do your labeling. So that's something we hope to dig into as well. So I'm happy to take any questions or hear about similar work or anything you guys want to talk about. Thank you very much.
Thanks, Stephanie. That was a brilliant presentation. Really, really interesting. So we hand over to questions now. We've got about 20 minutes or so. I think there's one question in the Q&A so far, but please continue to, another one's been added. So I'll start going through the questions and
okay, good. If you could read them, that would be helpful.
Great. So first question from Michelle: why would E perform less well than D? Was condition E always performed at the end?
I'm sorry, let me see if I can close this. Dismiss. Okay. Why? So I'm sorry, can you read the question again now that I've gotten rid of that?
So yeah, why would E perform less well than D? Was condition E always performed at the end?
So each annotator, maybe I didn't say this, that's on me, I'm sorry. Each annotator was in just one condition, right? So Stephanie, the annotator, was assigned to condition C, and Tim, the annotator, was assigned to condition B, say. So no, condition E wasn't sort of always at the end. So there was a random set of annotators assigned to condition E. I think sometimes when we see condition E doing less well in those learning curves, perhaps is what you're talking about. Those learning curves were the BERT model, and they were hate speech. And so I think what's going on here is that in condition E, hate speech was always collected at the end of condition E. Maybe that's what you're asking in the question. So we see fewer hate speech labels in condition E, right? We see a decrease here from D to E. And I think, and then when we look at that learning curve, sorry, I'm just gonna quickly go through here, we see that condition E in the hate speech and in the BERT model is lower. And so I think, again, this is another sign of that fatigue effect, that when they went through those 50 tweets again and were coding hate speech, hate speech was always the back end of that instrument, they were tired and they were doing a less good job. They were giving fewer hate speech labels, and maybe the ones that they were giving were just not good. Maybe, there's just a very low quality. And that's why the model is struggling here to learn and to get as good a performance as the other conditions.
Great, thank you. Next question, can the annotator select both hate speech and offensive language under condition A?
Yes, they can.
Yes. Yeah.
The one, not say one more thing about that. The one regret I have about that is we don't sort of have another version of A where we have offensive language first. So the response options were always ordered hate speech, offensive language, and neither. And you could select, it was sort of select all that apply, but obviously you can't select neither, and you get it. So it was always sort of in this order. Hate speech was the first option and offensive language was the second. I wish we had reversed those, because I think that explains sort of this column effect, and maybe the slight row effect that we're seeing for condition A is because hate speech was on top.
Yeah.
And we don't have the converse to test that.
Makes sense. I did just a related question, I guess, on condition A. To what extent do the annotators get kind of a briefing or instructions? I guess in the way that our interviewers do. It's a simpler task than a lot of maybe what interviewers will be doing. But I did wonder. It was an interesting. The question was, can they both be selected? Because I wonder, maybe are some people not sure if they can select both, or if they select one or the other, or maybe it's more effort to select both. So
right.
So are they kind of given any like briefing or instructions, or are they just kind of given the task and get on with it?
Yeah, that's a great question. They were given an instruction. So there were about 10 screens of instructions that walked through, like, by offensive language, we mean this. By hate speech, we mean this. And he gives an example. Here are examples of tweets that are offensive language. Here are examples of tweets that are hate speech. And then we show them, like, some tweets can be hate speech, but not offensive language. And some tweets can be offensive language, but not hate speech. And so we walk them through the definitions and we give them examples from that corpus of tweets that meet the definitions or don't meet the definitions. We also have examples of neither, tweets that don't have either of those. And then as they went through the instrument, there was a question mark that they could click on to see the definitions of the two terms again. We don't have paradata on how often they did that. I think from the survey methods world, we suspect they probably don't click on that a lot, but it was available. What we didn't have was instructions on like how to do a web survey, right? So I don't think we explicitly said, like, you can click both hate speech and offensive language in condition A. We had the radial buttons, which are, so which the check boxes or whichever one it is that's meant to suggest that you can click more than one, is what we use. But I don't know that we explicitly told them that they could select both there. Okay,
cool. Yeah, I kind of wonder whether if you had like a both button, maybe have like 4 single choice. So offensive language, hate speech, both, neither, whether that would produce any different results. I don't know.
Yeah.
Right. So some more questions. I'll stop talking. Question from Silver: could the survey methodology be applied since the start, even in the selection of the annotators themselves?
Yeah, I think that I'm not exactly sure what you mean by that, but I think it's probably the last point I was making in the presentation about the next step is that we'd love to study whether it matters how carefully you control the annotators. And there is some work on this in the machine learning world. They know that they need to have, they do a good job of having representative annotators. There's some crazy study where somebody had used annotators from a specific platform that was like really cheap. And it turned out that they were, for some reason, this platform is like majority of them are Venezuelans working in Venezuela. As you know, the economy there is not good. And so people are looking for tasks they can do online to make some money. And I'm sure they're doing a good job, but like they're not native English speakers. And so the tasks that they were given, they didn't do a great job on because their English wasn't sort of up to what was needed. So the machine learning field has realized that they need to do a good job of understanding who's doing these models or doing this annotation and choosing a representative sample. And of course, there's a lot of research about like, you need to have a diverse sample, right? Like you can't just have like white college students doing your labeling. You need to have a sample that represents the broader population. So some of that I think they're aware of, but yeah, I do think that's an interesting area for future research.
Great, thank you. Got a few more. So Thanks for the presentation. I was wondering how many tweets, straight images, straight annotations, annotators would usually be asked to code in machine learning projects? Around 50 such in this study, and did you look at the different performance times per annotator?
Difference performance.
So different performance times. So I guess how long it takes annotators to complete the task, whether some are quicker than others.
Yeah, we have that data, but we have not looked at it yet. And we also collected annotator characteristics. So like basic demographics, we asked them about their social media use, about whether they'd been bullied online, sort of getting at like how sensitive are they to hate speech and offensive language, to ask some questions to get into that kind of stuff. We haven't looked at any of that yet to correlate it with this sort of what we're showing here. Unfortunately, we haven't done that. But the first part of the question, I'm sorry, can you remind me what that was?
Yeah, so how many tweets, images, or annotations annotators would usually be asked to code in machine learning projects?
Well, most of the instruments that I've seen, so like the actual annotation platforms, we have been using survey platforms to do this work, because that's where we can kind of carefully control how it works, how the tasks operate. But most annotation platforms, custom built to do annotation, they just serve up one task, like one tweet coding in this example. And an annotator logs in, does maybe the introduction, the training module, and then starts coding tweets and just goes until they get bored, right? So it's very much a pay per piece model. Like every tweet that you do, you get 35 cents or whatever it is, right? And you might do 2 and decide this isn't for me. I don't like these tweets. I don't want to read them. Or you might sit down and do 1,000 because you need some money to go out for, you need some money for something, right? So you need to do a lot of them. In the annotation world, there isn't this sense of, sit down and do a fixed amount and then you're done. We have always done it that way because that's how the survey instruments work. And because we like to sort of more carefully control the environment. As we know from interviewer effects, right? You don't want one interviewer doing all of your interviews because that leads to increased variance in your data. So that's why we've kept it to 50 in this study.
Okay. I guess as well, because you talked about the sort of fatigue effects, maybe with like condition E. I mean, I guess that could happen between projects. Presumably they can like code multiple projects on the same day. So yeah, if they're doing lots and lots on the same day, you might suspect that the quality of it is kind of worse later on.
Right. And you can't control for that. We do ask in our data, we asked like how many labeling tweets do you do, or labeling tasks do you do per month?
Okay.
Yeah.
Okay, another question from Debbie Collins. Are you planning to look at testing models that take account of the language in which the data, e.g. tweet, and codes, e.g. hate speech? I'm alluding here to if there are cultural differences that we see in survey response patterns.
Well, all of our tweets were in English, and we restricted the annotators to the US because we felt that would control a bit for cultural understanding. When the tweets were not necessarily from the US, we didn't have that information, but we felt like the majority of tweets are. And so that's why we kept the annotators to the US. We haven't looked at applying this in other languages or cultures at all. I think that's interesting, but we haven't done any of that.
Okay, great. Another question, to what extent can we attribute the difference in results to variances in the models versus the variations arising from different individuals filling out distinct surveys?
So you're talking about, let me see if this answers the question. We do have these annotator characteristics, gender, race, age. I think we have something like region in the US. We have sexuality. And so we looked at all of the annotator characteristics across the conditions. Annotators were randomly assigned to the 5 conditions, so you wouldn't expect that we'd have more like Asians in one condition or more men in another or anything like that. So in expectation, they should be balanced, but we also did check for the annotator characteristics that we have and found that they were balanced. So we're not too worried about that.
Great, thank you. We still got about 10 minutes to go, so if anyone's got any more questions, please type them in. Maybe just while we're waiting, I guess I was wondering, maybe it's a bit early for this, and you said you're going to reach out to the kind of machine learning community, but has there been much interest in any of the work you've done so far in the community? I mean, it seems like it should be of lots of interest when you have that Sam Altman quote at the start about bias of human feedback raters. It seems to speak directly to that. So has there been kind of much interest and interaction so far?
Yeah, we gave a presentation last year at the HCI conference, Human Computer Interaction Conference. And we got some good feedback there. We published a paper in their proceedings. To be honest, it's so hard to work in a different field, right? To say to a different field, like, hey, you should really be paying attention to what we do. I strongly believe that. And the few interactions that I've had, I think I can convey that. But it's hard to just like know what are the right conferences to go to. The conferences they have are really different, right? You have to months in advance submit a final paper, right? Not just like an abstract like we do for APOR or Ezra or other ones like that, right? And then you show up and you talk to people. You have to have the whole thing done like months in advance. It gets reviewed. It's like it's a different world, and it's a higher bar for that. I like to do it that way. That's why we're writing this paper really in a rush right now, and why I say we're going to have it done by the end of the month, because we're submitting it to a conference, and that's how it works. So I hope that we can get that done. So you have to write a paper quickly, but also really well so that it goes through review. So we're still honestly working our way through like how to do that and how to make a splash in these conferences. One-on-one, the interactions that I've had with machine learning folks have gone well, and I think we're on to something that they're going to be interested in. Sorry, I don't know why the doorbell's ringing. So it's still early days, but I think I'm optimistic that we're going to get their attention on this. I think they know that they are sort of operating blindly when it comes to data collection, right? I've met data scientists who said like, you know, all I want to do is train models and like tune hyperparameters and use the latest and greatest models from GitHub. But the first step is always like, go out and collect some labels. And I don't know how to do that. And so they're making a bunch of these decisions about how to structure the task, right? Should it look like this? Should it look like this? Should it look like this? They're making those decisions sort of blindly and honestly without any preparation or training, right? So that's what we can bring to them.
Yeah, great. And I guess even if decisions are being made, I mean, maybe it's just done at an organization level. And as you said, I think the need for kind of guidelines for the sector as a whole. So you've got what one organization is doing is kind of in line with what others are doing. It's been done in a consistent manner.
Yeah. Yeah, that's where we'd like this to go, is best practices. And that's where we are in the survey field. We know that you shouldn't ask questions in certain ways because you're going to get different answers. And we know a bit about what like order effects, when's that going to happen and stuff like that, which is very early days here, right? We're still figuring it out.
Yeah, great. Okay. Oh, I think I was just going to say we don't have any more questions, and then one more came in. From Jacob, was the effect of the annotation method smaller when using a pre-trained model?
No. So this is the differences in the Rocket UCs for the LSTM, which is the not pre-trained model. I guess I haven't actually quantified like how do these things different. This is a 5 percentage point difference. Here we see a 4 percentage point difference. I'm just sort of looking at like the maximum minus the minimum across the rows here. We see a 4 or 5 percentage point difference. If we look at BERT, they're about the same, right? 79 to 83, 84 to 89, 84 to 89. So I don't think that we have smaller condition effects in BERT versus LSTM. But it's a good question. We can look at that more rigorously.
Thank you. Right, last chance for any final questions. I'll give a few more seconds for anyone to ask anything. One more is coming from Debbie again. So thinking about what this might mean for training models, is it realistic to think that one model can be applied to all data on a particular topic? Do we understand enough about how these models are operationalized?
So do you mean like maybe an approach going forward is to use a couple of these conditions? It's like use B and C or B and D and E, rather than trying to like putting all our eggs in one basket and using just one approach, trying to average over these models by using more than one, or to average over the different condition effects by using more than one condition. Yeah, that's an interesting idea. We haven't done that. We could train a model on all of the conditions and evaluate it against all of the conditions and see how that works. We haven't tried it, but I like that idea.
Okay, great.
Yeah, 2 more.
Yeah. Yeah, so Debbie said yes, or different models for different countries.
Different countries. Okay, yeah.
And a question from Lucilla. Thank you for the talk. Very important work. Do you think that this could have consequences on the racial / gender biases we're seeing AI models have so strong? Could better labeling help adjust these?
Yeah, that's something I have been thinking about lately as well. I'm sorry, I'm thinking about a specific, something I just read from Andrew Ng. I don't know if you guys know who Andrew Ng is. He is big in the AI field, particularly in what he calls data-centric AI. I believe he developed this term called data-centric AI, which suggests that like, hey, maybe we don't need to mess around with like the latest and greatest models and, you know, tuning the hyperparameters ad infinitum to get a tiny bit more performance. Maybe we've gone like as far as we can go with that, and the marginal benefit is decreasing, right? And isn't where we should put our effort. Instead, what we should do is collect better training data. And so I love the sense of data-centric AI, because that's what I do. That's what we do, right? Is like, yes, we can help you collect better training data. That's where to put the money. That's where the big gains are, right? Now, some people are saying, because of these large language models like GPT-4 and its buddies, right, that we're not going to be doing label collection anymore. We don't need to go out and collect labels from humans, because we'll just have GPT-4 label our data. And there have been a lot of studies recently saying the end of label collection, or GPT-4 can collect all your labels for you. It's already like, it's like BERT, right? It's one of these models already trained, already spun up, and knows a lot of things. And so rather than fine tuning that model, like it's good already the way it is, we'll just ask it, is this tweet hateful or not? Or is this tweet positive or negative sentiment, or things like this? I've been a little bit worried about those reports, because, you know, having just done all this work about how to collect good labels, if it's now the end of labeling and people aren't going to do this, then nobody's going to care about this work anymore, right? However, what Andrew Ng said is like, going forward, the labeling that we're going to be doing is exactly the kind of stuff that this question asker just asked about, right? Like, we're going to need to collect labels about, is this ethical? Is there a discrimination in the results from this model? Do we need to get like a diverse sample of annotators to look at results and tell us whether there's something fishy going on in the model. So that's exactly where the labeling is going to go in the future, is we're going to need good label collection from a good diverse sample of annotators to give these models feedback about whether they're doing things that are inappropriate or unethical or discriminatory. So I think that's really the future of labeling. Is there an interaction between that kind of labeling and the conditions? We haven't looked into that, right? Like, we haven't looked at what's the best way in terms of these different kinds of conditions, and the many other conditions that we didn't test, right, to collect information about model discrimination, that kind of stuff. We probably should pivot to that, because if that's where that's where labeling is going, then we should be able to talk to that more clearly, but that's not what we've done yet.
Great, thank you. I think that's no more questions coming in, and we're nearly at the finish time, so I think we'll close there. So thank you so much, Stephanie. That was a fascinating talk and a great discussion as well, and a really great way to mark our 50th event. So thank you very much.